In addition to partial derivatives, we're just looking at whether or not we integrate with respect to x, respect to y. I'm sorry, not partial derivatives, partial integrals or partial antiderivatives. We talked about whether we're integrating with respect to x or respect to y. But now that we're dealing with multivariable functions, we can also consider what are referred to as double integrals. So what we mean by a double integral is that in a first step, we integrate with respect to x, and then in a second step, integrate with respect to y. Or we could flip that around. We could first integrate with respect to y, and then in a second step, integrate with respect to x. So essentially a single problem is going to have two iterations of integration, and in each case, we're going to integrate with respect to one variable or the other. So we can define a double integral for some function f of xy, where a is less than or equal to x, is less than or equal to b, and c is less than or equal to y, is less than or equal to d. So this part we're used to seeing x is bounded between a and b, which gives us the bounds for our integral, our definite integral. So now we're introducing two new letters as the upper and lower bounds for y when we integrate. So then the double integral of f of xy is the double integral, so two integration symbols, of f of x comma y dA. So the a here just kind of is a shorthand notation. We'll expand this out a little bit more in just a second. But dA just means we're going to complete both of these integrals with respect to one variable than the other, and we're integrating over some region R. And in this case, that region R is defined by these two inequality statements. So this is sort of the shorthand, the more compact notation for writing that, but we could expand this out and write it as the integral from a to b, the integral from c to d of f of xy dy dx. So we have two integral symbols, two expressions that tell us which variable we're integrating with respect to. And what we want to do is, even though we don't always write these brackets in, is sort of think of a set of parentheses around this interior integral statement. So all the way back to basic algebra order of operations, we want to work what's inside the parentheses first. So the first thing we'll do is completely evaluate this integral. We'll come up with some result, and then we'll complete this second definite integral that's now with respect to x. What we can point out, though, is that the order of the integration doesn't matter. So here we're integrating with respect to y first, and then with respect to x. But we could also flip that around and write the integral from c to d of the integral from a to b of f of xy dx dy. And again, if we insert these brackets that we don't normally write, but to kind of indicate to ourselves we're first going to complete this interior integral. In this case, first integrating with respect to x, and then integrating with respect to y. These two results will be exactly identical. So it doesn't matter which variable we integrate with respect to, x or y first, as long as we make sure the right values here are paired up. So in this case, x is between a and b, so if we're integrating with respect to x, we want to integrate from a to b. Then when we integrate with respect to y, we should be looking at the interval from c to d, since y is defined on that interval from c to d. So using this idea, we can also look at an application. In this case, an application that we've seen before, which is average value. But now we're going to deal with this for multivariable functions. So the average value of some function f of xy, where a is less than or equal to x, is less than or equal to b, and c is less than or equal to x, c is less than or equal to y, is less than or equal to d, can be calculated as 1 over b minus a. So this is already looking like the average value formula that we had before, but in that denominator we're also going to multiply by d minus c, and then that double integral over some region, which is again defined by these inequality statements, of f of xy dA. So keeping in mind what we just established, that we can integrate with respect to either x or y first, we can rewrite this problem in two different ways. So we could rewrite this as 1 over b minus a times d minus c, the integral from a to b, the integral from c to d of f of xy. So since c and d are that interior integral, first we'll integrate with respect to y, and then the second integration will be with respect to x. Or we could flip this around and first have the integral from c to d, then the integral from a to b of f of xy dx dy. So again, in each of these cases, all we're doing is changing which variable we integrate with respect to first, whether that's x or y. And as long as we keep those bounds of integration tied to the right variable, a and b should be tied with x, c and d should be tied with y. As long as we keep those pairings correct, these two results will come out to be exactly identical.